Of the 23 grid-connected generating plants in operation currently in Nigeria, with a total installed capacity of 10,300 megawatts and available capacity of 6,000 megawatts, fossil fuel-based thermal gas-fired power plants account for a total installed capacity of 81% and 82.5% of available capacity. Renewable energy utilization, efficient energy use, and reforestation are the key most cost-effective energy-saving and carbon-reducing opportunities. Energy efficiency and renewable energy are indeed the twin pillars of sustainable energy. Renewable energy sources, particularly solar and wind, are clean and environmentally friendly, non-polluting and non-hazardous. There are, as yet, no known environmental hazards associated with the utilization of almost all developed renewable energy applications. The ecological problems associated with the depletion of the forest reserve for use as fuelwood can be ameliorated by a planned program of reforestation with its inherent advantage of carbon sequestration. Yes. Very determined mobilization. I hope you surprise this time. This entails an imperative on energy conservation and a very determined mobilization of renewable energy. Complete reliance on renewable energies may not be realistic in the near future, but it is anticipated that they could have considerable impact in the preservation of the global environment in the next century. As it is estimated, they could account for more than 65% of the world's energy needs in 2100. Table 3 and 4 compares the carbon footprint of various forms of energy generation. These show that hydroelectricity, wind and nuclear power produce the least carbon dioxide per kilowatt hour compared to any other electricity source. Wind power and solar power emit no carbon from their operation. However, they leave a footprint during construction phase and maintenance during operations, which over a long period of operation becomes negligible. Hydropower from reservoirs also has large footprints from initial removal of vegetation and ongoing methane generation. Though they have little or no carbon footprints, the continued utilization of nuclear energy poses enormous environmental threats associated with this of any sustainable energy policy. Efficient use of energy, simply referred to as energy efficiency, has the objective to reduce the amount of energy required to provide products and services without compromising quality. There are a wide variety of energy-saving or efficient practices and devices. Indeed, enormous amounts of energy could be saved by energy conservation practices through behavioral change. Power management systems also reduce energy usage by turning off idle appliances or putting them in low energy mode after a certain time. Daylighting is the practice of placing windows or other openings and reflective surfaces so that during the day, natural light provides effective internal light. South-facing windows for the northern hemisphere are recommended for improved daylighting. Particular attention is given to daylighting while designing the building, when the aim is to maximize visual contact or to reduce the energy needs. Substantial saving can also be achieved from reduced use of artificial electric lighting. Artificial lighting energy can be reduced by simply installing fewer electric bulbs. Because daylight is present. or by the dimming or switching off electric lights automatically in response to the presence of daylight. I usually will give this example. What engineering does is to mimic nature. And nature has provided daylight. I consider it madness that during the day people light up, who use electrical power to light up an environment. So why don't we maximize daylighting and then use it only at night? Compact fluorescent lights, commonly referred to as energy-saving efficient lamps, reduce significantly the amount of energy required to attain the same level of illumination compared with traditional incandescent light bulbs. Due to their higher efficacy, CFLs in 2010, replacing all incandescent lighting with CFLs would assuming a conservative estimate of 20 million houses in Nigeria, using say 400 watts of incandescent, 40 watts of incandescent lamps. A 70% saving by replacing all incandescent lamps with CFLs in Nigeria will result in a net energy saving of 5,600 megawatts, more than 50% of our current total installed generating capacity, only from saving in lighting. Passive solar designs, passive solar energy design concepts are not entirely new, and date back to early civilization. Early civilization is, as can be seen from Socrates' description of vernacular architecture. And according to Socrates, says, now the houses are cast. The sun's rays penetrate into the body of the builder. But the sun at the top of the sun is right overhead, right over our heads and above the roof. If then this is the best arrangement, one should build the south side lofted to keep out the cold weather. That's Socrates 400 BC. Sustainable architecture can significantly reduce carbon dioxide emissions. This challenge is the carbon footprint of the built environment. Passive systems are simple, have few moving parts, and require minimal maintenance and non-mechanical systems. Most of the literature pertaining to passive solar energy technology address heating concerns that are most useful and relevant in temperate regions. Cooling issues, which are important locally, are less well documented. And I think it is important that I also mention some of the things from inadequate drying due to adverse effects of dust, unexpected downpour of rain, and other weathering effects, fungal attacks, insect infestation, pests, and rodent encroachment. Output is low and can be of very poor quality. Dried products are often degraded seriously, sometimes beyond edibility. Thus, a large proportion of the world's supply of fruits and vegetables continue to be sun-dried in the open under very primitive conditions. Under such conditions, solar energy dryers appear increasingly attractive as commercial propositions and viable alternatives. With Brian Northam, we established for the first time a systematic taxonomy of solar energy dryers that is now widely adopted internationally in classifying solar dryers. Two generic groups of solar energy dryers are identified, namely passive or natural circulation solar energy dryers and the active or forced conventional dryers, often referred to as hybrid. Three subgroups of these dryers are also identified: the integral type, distributed type, and the mixed mode. We established the appropriateness of each design type for application by rural farmers, particularly in developing countries. Did you show the figures? Okay. We also established a concise comparative analysis of the fundamental principles and theories governing the drying of agricultural products. We also outlined the chronological development of the purely theoretical, semi-theoretical, and empirical models, showing the shortfalls of the purely theoretical models in predicting accurately the exact processes involved in drying due to oversimplification of assumptions. We established that empirical models for specific products and conditions offer better predictions. Our novel work on linear correlations between crop drying rates, measured experimentally, and a group of ambient and initial crop parameters is the underlying concept that may form the basis for the development of solar dryer design charts. When drying a crop, it is essential that the safe storage moisture content is reached before decay processes start. Thus, a rapid drying rate is sought. This also facilitates a greater utilization of the dryer. However, if drying proceeds too rapidly, case hardening ensues, i.e., the crop forms an impermeable shell which prevents further migration of moisture from the interior, and then decay would start. Consequently, upper and lower drying limits can be defined for particular crops under specified conditions. Bearing this in mind, we sought to relate ambient and initial crop conditions to drying rate. The primary ambient conditions that would affect drying rate in a solar drying process are the level of insolation, ambient air temperature, relative humidity, while the major crop property that affects drying rate is the initial moisture content. Thus, can you show equation 1? Thus, we have that in equation 1. We found that for a particular dryer studied under the specific conditions encountered, the drying rate measured experimentally correlated linearly with the term in equation 2. Yeah. Consider figure 6. Can we go back to figure 6? Yeah. Which is a schematic illustration of a possible design chart from these correlations. For a given crop and climate, a particular predominance of G values can be anticipated. These are assumed to fall between G1 and G2. Furthermore, acceptable lower and upper drying limits can be defined, i.e. D1 and D2. Thus, only a dryer whose performance falls within these specified limits, i.e. the operating region, is appropriate. Thus, for the operating region indicated in dry B, it is the optimal design. Thus, graphs such as figure 6 may form the basis for farmers and agricultural extension workers to decide readily whether a natural circulation dryer is suitable for a particular geographical location. With Heinzel and Godev, we performed computational fluid dynamics calculations on a thermohydraulic flow distribution for a stack-induced natural circulation of air in an indirect solar energy dryer with distributed flow resistance and supplied with air warmed during its flow through a low-pressure drop thermosymphonic air heating collector. The calculation results of interest were employed successfully to make design modifications to the model towards actualizing desired effects. And thermal storage, due to the intermittent nature of renewable energy sources, storage in renewable energy applications is inevitable. Thermal energy stores are used for heat storage during periods of excess availability, for use during demands when availability is not guaranteed. With Howard Njoko and Sam Onyegebu, we developed a novel criteria for predicting the performance of stratified sensible thermal stores. For solar cookers, standard rating procedures for the performance of solar energy cookers had hitherto been non-existent. Solar cookers have generally been rated previously by test procedures that are dependent not on unique solar cooker properties, but on climatic parameters. Within Adesu work, we verified and confirmed novel, reliable design and performance rating criteria for solar cookers. Two figures of merit F1 and F2 are unique cooker design numbers for any given climatic condition. With Howard Njoko, Nkiru Dabara, and Anthony Nadozie, we showed remarkable improvement in the efficiencies of solar pumps and solar energy cookers using reverse side absorber plate to achieve significant thermal losses through convection suppression. Energy performance. Energy building codes for Nigeria are currently notoriously unavailable. With Chinwe Sam Amobi, who recently studied the effectiveness of the architectural design on energy consumption of hotel buildings. Our study may form the basis for the establishment of a most desired indigenous energy building code for Nigeria, which are currently unavailable. Some of the things we are currently doing or plan to do include energy performance research on the built environment and passive solar energy architecture, where we are studying the energy performance of a variety of purpose-built buildings, PV system failures, where we are investigating why PV installations fail in Africa, PV panel cooling, where we are investigating both theoretically and experimentally measures that may reduce excessive operating temperatures of the PV cells. Okay. Conclusion. Renewable energy technologies are essential contributors to solar energy as they generally contribute to world energy security, reducing dependence on fossil fuels and providing opportunities for mitigating greenhouse gases. Gazing at the crystal ball, the need for the concerted development of renewable energy-based systems and their integration into our national energy mix cannot be overemphasized. For sustainability in energy, improved and consistent dependence on renewable energy sources are imperative. On 26 November 2015, Nigeria submitted its intended nationally determined contribution to the Paris Convention and committed itself as party to the Paris Agreement on the United Nations Framework Convention on Climate Change of 2015. The country has been, in the course of the INDC, the nation committed itself to the following targets: reduction of up to 2 degrees centigrade in its environmental temperature, and the national energy consumption mix of 5% contribution from renewable energy. The actualization of these targets is dependent on realizable technological, social, and legal imperatives for concerted transition from over-reliance on conventional energy sources. Accordingly, we recommend a comprehensive one-stop legislation on promotion of renewable energy utilization and environmental sustainability in Nigeria, with definitive prescriptions on incentives as part of enforcement provisions on renewable energy development. And I think renewable energy applications, I say, are cheap because there are no costs at all involved in exploration, mining, or processing into an immediately usable form, as in conventional sources. They are clean because they are environmentally friendly, non-polluting, and non-hazardous. This is particularly so for solar and wind energy. They are in harmony with nature because they occur abundantly, naturally. They are in agreement with nature, and their exploitation does not offend nature and environment. I intend to acknowledge some people who have made some meaningful contributions to my career. To Donald Nadozie and Rose Ekechukwu, beyond giving me life, nourishing it and nurturing it, You taught me discipline and confidence. May their souls and the souls of all the faithful departed, through the mercy of God, rest in peace. I am so at ease because those who matter most to me also give me joy. To Nkiru, my beloved wife, you give me comfort. Very few would have tolerated my idiosyncrasies. To my beloved kids, Uzoma, Nnamdi, Uchennia, Chinwuchem, you have all been a bundle of joy. To my siblings, Frances, Emmanuel, John, Chinyere Nyeribe, and Angela, and their families, we have been a family so strong. We must continue to remember Euphemia in our prayers. To my cousins and aunts, for your prayers and support. I acknowledge Professor Brian Norton, my PhD supervisor at Cranfield. He had and continues to show so much confidence in me. He taught me to be firm, to be respectful and intrepid. I acknowledge Professor Joshua Fanero, my BSc supervisor at Ibadan. He taught me to do things right and avoid extremities. I also acknowledge my former teachers at Ibadan, who had great influence on me. Professors Iken Noyudo, Domingo Okori, Bibi Adeleke, and GOS Ikagore. Professor Fabian Osiji was my teacher, a great inspiration, a mentor, and a good friend. I acknowledge the warm support of Professor Bill Beckman, my host, during my Fulbright Fellowship at the Solar Energy Laboratory, University of Wisconsin-Madison, and Professor Sandy Klein, also of the Solar Energy Laboratory at UW-Madison. I acknowledge Professor Volker Heinzel, my host for Humboldt Fellowship at the Universität Karlsruhe, Germany, and Dr. Serge Godev of the Fortune Centrum Karlsruhe. Dr. Victor and Mrs. Vero Chilaka and their great kids have been so wonderful support to me and my family. I acknowledge Professor Emmanuel and his family. From the day in January 1985, we met at Mitchell Hall in Cranfield, we struck a friendship that has been most sincere and lasting. I acknowledge Erasmus Okoro and family for being family with me. I appreciate the true friendship of Professor Luke Anike and family dating back to 1983. I acknowledge Dan Juma Dati, my true friend and a brother.